No one uses school.
All right, good morning again, everyone. As you know, that the exam has been graded. Most of you did well, and some of you missed the practices and examples and end of chapter problems. As you could see, like the problems of the exam, mostly, in some cases I just changed some numbers from the end of chapter problem and from the examples that I was doing from the homework as well. So some of you did extremely well, actually, extremely well, and some of you missed like some trivial questions, like probability of certain event cannot be more than 100%. Okay, so probability cannot be 400%. So there is some trivial thing that you guys missed. So please pay attention to class, and also like this year most of the theory that I have, I typed some of the, in the previous years I had to write some theory, but all the theory mostly are actually typed in my slides. So you have enough information as far as the concept is concerned. If you simply read my slides with matching with the books a little bit, you guys should be fine. But examples, I don't have all the examples typed. So I go through the examples. Make sure you pay attention to class and practice. Like it seems that this course, it's not that easy course either. Okay, there are a lot of data, a lot of formulas to remember, and also those formulas, some formulas you don't need to remember. Those come from just some trivial equations that, for example, probability of finding certain events, given the outcomes in the event, and if you know the sample space, you should know what is the probability, and that probability should be between 0 and 1. Probability cannot be more than 100%. So you now know the format, so be prepared for the next exam, and throughout the semester I will be giving you some extra credit problem as well. Those are easy Python related mostly. So please do pay attention and practice accordingly. So we need to move faster a little bit because we are behind 2 lectures actually. Today we start from PDFs of continuous random variable. Okay. PDFs of continuous random variables. Probability density function of continuous random variable. But for discrete, if you are given the CDF of a random variable, okay, the other true false type question, guys. True false type question. CDF of a random variable x. This random variable could be both discrete or continuous. So CDF, cumulative distribution function, can be used for both discrete and continuous random variables. When you find the PDF, it's basically you take the derivative of the cumulative distribution function to get the PDF, probability density function. Now, we wrote CDF of a discrete random variable using CDF of a discrete random variable using unit step function x minus xk. Okay? When you take the derivative, if you take the derivative of this CDF f sub xx, okay, I have it here already. So if you take the derivative of the CDF, you keep this PMF, and what is the, guys, can you guys tell me what is the derivative of the step function? In engineering, mathematicians, they will say that step function is discontinuous. Okay, so if you have a step function like that, so we have a step function like this. So this is e sub e of x, and this is x. Okay, mathematicians, they will say that, okay, so here this derivative does not exist because there is a discontinuity here. There is a discontinuity here. But in engineering, we do find that there exists a derivative of this unit step function. So the derivative of unit step function is basically delta of x, delta function. It is called delta function. And delta function, I don't think that is new in discrete random variable. 301. You guys heard about delta function? 301, yeah, delta function. So this delta function basically is the derivative of the unit step function, and the property of delta function is that at x equals 0, at x equals 0, you have infinite I put an arrow right here. At x equals 0, the value is infinity. So that mathematically we write delta x is infinity when x equals 0, and it is 0 otherwise. Okay? It is 0 otherwise. It is used to find the strength, the power of a signal. Okay, so that's the physical meaning of a delta function. Now we are going to use this delta function to denote the probability density function of a discrete random variable. But for continuous case, we can actually use this delta function. If we integrate from negative infinity to positive infinity, if we integrate the delta function, we get the unit step function. So there is an example. I'm just going to put this as this example as the homework. Now we are moving on to the most important topic of this chapter, which is the Gaussian distribution function. It is the most important topic, and there will be problem on this topic in the exam. It's guaranteed. So this is the most important topic of this entire chapter, Gaussian distribution function, and we will be making use of this a lot. And engineers, electrical engineers, cannot think anything without this Gaussian distribution. In every aspect of engineering, this Gaussian distribution function. It's so important that even though you don't know the distribution of certain random variable, we absolutely have no idea. Then given the data, we can still approximate that random variable as a Gaussian random variable. It's very, very important. And you guys know about this bell-shaped curve already. I'm so bad at drawing, so that's why I use computer. Okay, so a bell-shaped curve like this. you guys probably know about it. So here, this bell-shaped curve is actually probability density function of a Gaussian random variable. Probability density function of a Gaussian random variable. It's probability density function of a Gaussian random variable. And why I say Gaussian random variable, because the scientists actually came up with this sort of distribution when we actually shape this distribution with two parameters. So one parameter is called the standard deviation, the other parameter is called the mean of variable. Now this axis, this horizontal axis, is basically your random variable. So you take many measurements, measurements of random variable X measurements. You see around the mean, if you compute the PDF, probability density function, this probability density function will have a single peak. If you have a single peak and the width, you can actually shape, you can control using sigma. This sigma is called the standard deviation. Standard deviation, and this mu is the mean. Mean, which is mean of random variable X, standard deviation of random variable X. So this mean we find using the expectation operator. Expectation of X. Now, this shape has a closed form mathematical form. So f sub x is basically 1 over sigma, which is the standard deviation, square root over 2 pi, and then you write e to the negative half x minus mu over sigma, mu sub x over sigma sub x. As you vary x, you can actually see that you will be able to plot it exactly like that. And in Python, there is in Python you can import this random variable from statistics package. It's called SciPy from SciPy dot stats import not. It does not call it Gaussian distribution. It's called normal distribution. Okay. So the word normal distribution. And Gaussian distribution, the same thing. Gaussian distribution. So please do not get confused. So normal distribution and Gaussian distribution, they are basically the same thing. So this is a little explanation, and I also drew plots in the following slides. So because this Gaussian distribution, also called normal distribution, we write a random variable follows Gaussian distribution or normal distribution using this notation. In many books, many research papers, people use this calligraphic letter n and denotes the normal distribution with two parameters, mean and variance. Mean of random variable x and variance of random variable x, which is sigma squared, where sigma is the standard deviation. Now, given this distribution, you can actually find the probability of a random variable x that takes values between 1 standard deviation less than the mean and 1 standard deviation more than the mean. In this range, what will be the probability. And this probability you can find it using integration. And this integration is not trivial. You cannot actually do the integration. Okay? This integration is not trivial. This integration is not trivial, which means that there is no closed form solution. And I'm going to talk about that in a moment. So you just change the limits of the integration mu minus sigma to mu plus sigma. You change the limits of this integration to get this probability of three different ranges. Okay, mu minus 3 sigma to mu plus 3 sigma. You just change the limits of this integration. Now, as I say, that since there is no closed form solution, you simply cannot integrate this probability density function, which follows probability density function of a Gaussian random variable. Since you cannot simply integrate, there is a way that you actually use numerical integration. If you use numerical integration, you can actually see that probability that your random variable takes values one standard deviation less than the mean and one standard deviation more than the mean. You can numerically integrate and you will see that it is 0.68. And similarly, you have other two probability of other two intervals. You see that it is 0.95 and 0.9. And if you actually numerically integrate, you see that nicely I colored where the 68% fall, where is 95% fall. So probability that a random variable takes value between mu minus sigma to mu plus sigma, it is 68%. And 98% is from this point to this point. You will see that 98% of the measurements will fall in this range. And there will be a computer experiment here. Did you have any question?
Does it matter does it matter what you're using for your mu and sigma values for the integration approximation or no?
No, it doesn't matter. As long as it follows Gaussian distribution, doesn't matter the value. Okay? So all what you see, that's why I did not put any specific value here. Okay? You can have any value, but all what this mu is doing, mu is actually shifting. Very good question. Actually. Mu is actually shifting this peak. The role of this mu is to shift the peak left to right. Okay? And the role of sigma is basically control the width of this distribution. Okay? Does not matter what mu and sigma is. You will see if you do the integration, it is going to be constant, close to 0.6. Okay? Because there is no analytical solution. Like whatever you learned in Calc 1, okay, that integration method, no integration method will be able to solve it. So only one solution you have is numerical integration. And numerically, you can find that probability that your random variable will take values between mu minus 2 sigma to mu plus 2 sigma. Okay, it is going to be 0.91. And then you will have a computer experiment for the computer assembly for that, and you will see practically. Okay. So now Gaussian integral. This integral, guys, you will have a little bit of practice. For any x from the real line. Okay, for any x in the real line. E to the negative x squared is called the Gaussian function. E to the negative x squared is called the Gaussian function. And if you integrate e to the negative x squared dx, it is going to be square root over y. Okay. Now, what I'm going to do, in your lifetime, this is the only time I am going to show you that how this integration is square root over pi. I'm going to go through the details of derivation now. And this derivation will not be in the exam, and in your lifetime, you will never use this integration. All what you will do, that you know that this Gaussian integral is square root over pi. That's all you will need. But in your lifetime, the derivation that I'm going to go through, there is a proof, okay? So this is the only time you know that, okay, this integration is square root over pi, but from after that, like you calculate the mean, variance, okay? You will be using this result, but no derivation. And this derivation is not a math class. This derivation, I'm just showing you that in your lifetime, you know that this Gaussian integral is square root. So let's do that. Okay? So you can do this integration with me. Go. Proof. So this proof, the main objective is that we are going to show this integration is square root over pi. It's a good practice, guys. Try to understand how we do. I equals integration negative infinity to positive. I'm going to assume I equals e to the negative x squared dx, and from there I'm going to write square. I'm going to square it, and it is going to be negative infinity to positive infinity e to the negative x squared dx squared. And I can actually change the variable and call it integration negative infinity to positive infinity e to the negative x squared dx. This is one term, and I can multiply with the same term to get the square. But this time I'm going to change the integration variable. Negative infinity to positive infinity e to the negative y squared dy. So I just changed the integration variable. That's all I did. So there is nothing changed. So now I can actually make this as a double integral. So I squared, I can just make it as a double integral where x goes from negative infinity to positive infinity, y goes from negative infinity to positive infinity, e to the negative x squared times e to the negative y squared. So you know that e to the negative, what is e to the a times e to the b? E to the, because e is, you have the base sense, so e to the a plus b, right? So that's what I'm going to do. So e to the negative x squared, e to the negative y squared, you can have e to the negative x squared plus y squared, and then you have dx dy. Okay? So I am going to show that this double integral will give you pi, and therefore that is going to be your I squared. Therefore I is going to be square root over pi, and that's what requires. That's what requires. I'm going to assume that it's a unit circle. No, it's a circle actually. It's a circle. This is your y, this is your x. Okay? And this radius is basically your r, and this is theta. This theta. This radius can go to infinity as x, y go to infinity, negative infinity to positive infinity. So this radius will go to 0 to infinity. Okay? So that's why we bring 0 here. Also, that's what we bring 0 here, and we limit the integration to positive infinity only. Okay? So that's one simplification. The other thing, we can have a definite integral, guys. See, this theta will vary from 0 to 2 pi. This theta will vary from 0 to 2 pi. So therefore, you can have, you can assume that x equals r cosine theta, y equals r sine theta, because I'm going to remove one end of the limit. I'm going to remove negative part of the limit. Okay, so I'm just going to put 0 to infinity. Because x varies from negative infinity to positive infinity, y varies from negative infinity to positive infinity. I am converting x and y in polar form just to have the limit of r from 0 to infinity and theta 0 to 2 pi. So here you will have limit r from 0 to infinity and theta from 0 to 2 pi. Okay, so like that, we will not have negative anymore. But now I reconnect again. Now we are left with this dx dy. What we are going to do? Look, guys. So I'm going to compute the Jacobian. I'm going to compute the Jacobian, which is dx actually I'm going to take the partial derivative dxy over partial r theta. So this is basically Jacobian. I take the determinant. You guys know what is determinant, right? So I take the determinant and this one is going to be your partial x over partial r, partial x over partial theta, partial y over partial r, partial y over partial theta. So this is going to be the Jacobian, and you take the determinant of Jacobian matrix. So this will give you partial x over partial r. So if you take the derivative with respect to r, where theta is constant, so you are left with cosine theta. And if you take the derivative of this quantity with respect to theta, you are left with negative r sine theta. If you take the derivative of this quantity with respect to r, you get sine theta. And if you take the derivative of this quantity with respect to theta, you get r cosine theta. Okay, this is just for you to understand. This derivation will not be in the exam. I'm just going to show you the proof why I wrote that Gaussian integral equals square root over pi. So if you take the derivative, you see that it is r cosine squared theta minus plus r sine squared theta. So you are left with r cosine squared theta plus sine squared theta equals r dot 1 equals r. Okay, so this Jacobian will give you r. Now the dx dy is basically your Jacobian over dr comma theta, Jacobian, and then you have dr d theta. So it is going to be r dr d theta. So now I squared in polar coordinate yield I squared integration. So you have negative infinity to positive infinity. Here you have negative infinity to positive infinity. And actually, guys, what you can do, so that you know there is another notation. So this double integration you can directly write R2. This R2 denotes in xy plane, you take the entire x axis, entire y axis, and you have e to the negative x squared plus y squared dx dy. Now, because of the conversion to polar coordinate, now we write this integration 0 to infinity. R goes from 0 to infinity, and you have 0 to 2 pi r d e to the negative r squared r dr d theta. So instead of dx dy, we came up with r dr d theta, and instead of negative x squared plus y squared, we have e to the negative r squared, because x squared plus y squared equals r squared. Now we are going to assume another quantity. So we let negative r squared equals u equals negative r squared. Actually, let's keep it simple. U equals r squared. So du equals 2 r dr. Which gives r dr gives du over 2. So, which gives I squared equals, let's bring, now we can do the integration, the other integration. So, integration 0 to 2 pi e to the negative u r dr is going to be du over 2. So you can bring half out of the integration, and it is du, and then this integration is going to be 0 to infinity again. U will vary, will go from 0 to infinity, and here you have d theta. Look, guys, this part you can evaluate it easily now. So half integration 0 to 2 pi. This quantity is independent of d theta, so you can just bring d theta here, and then integration e to the negative u is going to be e to the negative u over minus 1. You can put minus here. 0 to infinity. So this part will give you, this integration will give you 2 pi, and this 2 pi with this half is going to give you 5, and this limit will give you, you have infinity here, so e to the negative, negative infinity, e to the negative infinity is going to be 0, so this part is going to be 0 minus, and because of this minus it is going to be plus. You substitute u equals 0, so e to the 0 is going to be 1, so it is going to be pi. So I squared equals pi, so therefore I is simply square root of pi. Root. So I will be directly using this result in the upcoming slides, but for your lifetime, you know how to, you know that this Gaussian integral is simply square root over pi. And this derivation, as I said, that I will not be giving you this, I will not be asking you to prove that this Gaussian integral is square root over pi. So how to use that? The application of this Gaussian integral is right here. Look, I showed you this figure. So you have this bell-shaped curve, which represents the probability density function of a continuous random variable that follows Gaussian distribution, and this is where most people make mistakes, guys. Please make sure that you do not write the peak value this is where most people make mistakes. This peak value, it is not 1. It is not, this peak value is not 1. The peak is not 1. Here the peak is not 1. What is 1? You take the integration of this entire function from negative infinity to positive infinity. If you do the integration from negative infinity to positive infinity f sub x dx, this integration is going to be 1. This entire area is going to be 1, but not the peak. This peak is not 1, guys. This is where most people make mistakes. This peak is not 1, and this peak does not represent the probability. The probability is basically you do the integration of this area, then you get the probability. This peak, it is not the probability, it is basically the distribution of this function. This value of this curve at certain points, this represents the distribution of the random variable, but it does not, this y-axis does not represent the probability, it is the probability density function. And you get the probability when you integrate the probability density function with certain range. Okay, that's the key point here. And the total integration, and you will see a lot of homework examples. Okay, end of chapter problems. You will see the total integration is going to be 1. And how the total integration of this Gaussian random variable is 1, I'm not going to write it down. I typed it here in my slide. So I directly used the Gaussian integral. So look, so this integration from negative infinity to positive infinity, you substitute f sub x with its expression, which is a Gaussian distribution. Now you just let this quantity x minus mu over square root over 2 sigma equals 1, and then you take dy equals dx over sigma square root over 2. So your dx is going to be simply sigma square root over 2 dy. Okay. So now you use this result, you substitute right here. So you get 1 over sigma square root over 2 pi, negative infinity to positive infinity, e to the negative y squared, sigma square root over 2 dy. Now, you bring this quantity out of the integration, sigma square root over 2 pi. Sigma square root over 2 pi, you are left with negative infinity to positive infinity, e to the negative y squared dy. This is basically Gaussian integral. Which you can write square root over pi. So now it's a matter of just calculation. Sigma disappears, square root disappears, square root over pi, square root over pi, it disappears, you are left with 1. So the total integration of a Gaussian random variable, or total integration of the probability density function of a Gaussian random variable is 1. So this result you will be using directly in some of the homework problems. Now, I have standard Gaussian random variable. See, the topics that I'm coming along, so one topic is more important than the other one. Okay? So this Gaussian, standard Gaussian, I do not say Gaussian random variable. I say standard, the keyword standard. Look, the keyword standard. Standard Gaussian random variable, and when you import norm, okay, so import from stats package, you import norm module. This norm basically represents the standard Gaussian random variable or standard normal variable. Okay, so this norm basically represents the standard Gaussian random variable. Please pay attention here. So standard Gaussian random variable. There is a difference between standard Gaussian random variable and Gaussian random variable. Gaussian random variable, mu and sigma can be any value, but standard Gaussian random variable, mu is going to be 0 and variance is going to be 1. That's what differentiates between standard Gaussian random variable and simply Gaussian random variable. Standard Gaussian random variable, you have mean equals 0 and variance equals 1. It's fixed. Then you say that it is a standard Gaussian random variable. And standard Gaussian random variable, we denote it with 2 parameters, 0, mean and variance 1. It is this one. It is not standard deviation. It is the variance. The second parameter is the variance. First parameter is the mean. Second parameter is the variance. So that's why people write x as mu, comma, sigma squared. So sigma is the standard deviation, sigma squared is the variance. Now, if you substitute mu equals 0, variance equals 1, you see that the generic Gaussian probability distribution represented by this PDF is, because sigma equals 1 and mu equals 0, so you have 1 over square root over 2 pi and exponential negative x squared over 2, because you have x minus mu over sigma squared. Because mu equals 0, sigma equals 1, it is x squared, and you have negative half in front. So that's why you have negative half x squared. So the PDF basically is a bell-shaped symmetric. This is another keyword. Symmetric. This is the modification that I last portion. So this is a bell-shaped symmetric about x. So here you see that when you substitute mu equals 0 and variance equals 1, at x equals 0, so you see that it is simply 1 over square root of 2 pi. So at x equals 0, your PDF of a standard Gaussian random variability is 1 over square root of 2 pi. It is symmetric about 0. Now, this is basically mu equals 1 Here, this limit is basically x minus mu minus sigma, because mu equals 0, sigma equals 1, you write minus 1. So this is mu plus sigma. Okay, mu equals 0, sigma equals 1, that's why you have 1. And here you have 2 because you have mu plus 2 sigma. Sigma equals 1, mu equals 0, so that's why you see 2. And that is the reason I was able to exactly label the ticks here. Okay? So it is actually coming from the generic definition of Gaussian random variable. Now, cumulative distribution function of a standard Gaussian random variable. Look, this is another thing. So, cumulative distribution function, if x is any random variable, so we write f sub x is a cumulative distribution function, which by definition it is x less than or equals x. By definition. Now, when x is a standard Gaussian random variable, if x is a standard Gaussian random variable with mean 0 and variance 1, then this CDF becomes the standard CDF. So now we do not say CDF only, we say standard CDF. So this phi sub x is the standard CDF. In other words, we call it CDF of a standard Gaussian random variable. In other words, it is called CDF. I'm going to write it down. CDF of a, I'm going to use red color, standard Gaussian random variable. So this standard Gaussian random variable is a keyword, and CDF we already know, cumulative distribution function. So CDF of a standard Gaussian random variable is, because x is a continuous random variable, it is negative infinity to x instead of summation, we write negative infinity to x. It is the PDF, probability density function of random variable x, and this s is basically the integration variable, because x is some upper limit, I cannot write x here. So I just substituted the expression for f sub x right here to get the integration. Now there are some properties of this standard CDF or CDF of a standard Gaussian random variable. When x goes to infinity, this standard CDF is going to be 1. When x goes to negative infinity, standard CDF is going to be 0. At x equals 0,